Lenz's law before we get started. The first thing, which is really important, is so we're going to move the magnet near the coil, okay? And it's really a moving magnet near a coil, a closed loop, that's going to induce a current in that coil. Now that current that will be induced, let's just call it I, that is going to produce, or it's also going to induce, a magnetic field. And our job is going to find what is the direction of I and what is the direction of the induced magnetic field. So the second point that's really important for Lenz's law is the induced magnetic field will always try to keep the flux in the loop constant. So there's going to be two fluxes in the loop. There's going to be the flux due to the magnet that I'm pushing in, and then there's going to be the flux due to the induced magnetic field. And the key to remember, at least for the second point here, is that this induced magnetic field will always be such that it tries to keep the flux through the loop constant. So let's start with the first example. Okay, so here's our first case. So we have our magnet that's just in front of the coils here. So as it stands right now, if you are not moving the magnet, there is no current, right? Because case number one, or point number one, is not satisfied. The magnet has to move for there to be an induced current in this coil. If the magnet is just here in equilibrium, no one's moving it, there is no current induced in the coil. Now what we're going to do is we're going to take that north pole and we're going to move it closer. Okay? We're going to give it some velocity toward the coil. So what happens here? Well, initially what you have, now these field lines, I didn't kind of draw them too far here, but let's draw the field in that coil initially. So we have a certain amount of field B and a certain number of field lines that are crossing or going into, that are going through the coils. Okay. Now what happens when I move it in? As I move it in, what happens? Well, you're also going to push additional field lines. You're going to get more field going through the coil loops. Okay. So now let's look at case number two. Case number two says the induced magnetic field always tries to keep the flux in the loop constant. But I just showed you that I increased it when I move the magnet closer to the loop. So how would I keep it constant? I would keep it constant if I would induce a magnetic field that would oppose the delta B that I increased when I pushed the magnet closer to the coils. So this here has to be the direction of the induced magnetic field. So now that we've established this, all you have to do now is use the right-hand rule in order to determine what kind of current, what direction of current would produce a magnetic field that points to the right inside the loop. So the right-hand rule says you place your thumb in the direction of the current and you curl your fingers, and I want to curl them toward the center of the loop. And what you should find is that the induced current for this particular case, I, is going to be in this direction. You take your right hand, you place your thumb along I, and you curl inside the coil. You're going to find that the induced magnetic field is indeed pointing to the right. So therefore, you've obtained the induced current for this particular case when you push a north pole closer to a coil. All right, let's have a look at case 2 now. So when the magnet is simply in this position, well, there's a certain number of field lines that are going to cross or go through the coil loops. So we have a magnetic field going in this direction. Now what happens when I move the magnet? In this case, I'm going to move the magnet in this direction. I'm going to give it a velocity v away from the coil turns. So what's going to happen? Well, I'm going to get a delta. In this case, I'm going to get fewer lines. So I'm going to get delta B that's going to decrease the total number of field lines crossing the coil turns. However, remember the second point from the previous slide. What that means is that the induced field is going to be in a direction that tries to oppose that. Remember, Lenz's law says we always try to induce a magnetic field in such a way that we keep the flux through the loops constant. So that means we want to always be opposite of the change here of field, or the change in flux through the coil turns. So that means that in this particular case, my induced magnetic field has to be pointing to the left. Now, if you want to find the direction of the induced current, well, what kind of current would produce a magnetic field pointing to the left inside the coil turns? Again, you have to use the right-hand rule now, and if you place a current going in this direction, what you're going to find is that's going to induce a magnetic field that is pointing to the left. Again, you take your right hand, you place your thumb in the direction of the current, and curl your fingers, and when your fingers are pointing inside the coil turns, you should get a vector that is pointing to the left. Okay, now we have the south pole. We have a south pole. Well, the field produced by the south pole going through the loops is going to be, in this case, it points to the right. That's the field. Now, what happens when you push the magnet closer to the coil? What happens? You're really going to push more, right? There's going to be more field going through the loops, and there's going to be more field pointing in which direction? You're going to add extra field in this direction. So, what does that mean for the induced field? Well, the induced field wants to keep the flux inside the coils constant. So that means that the induced magnetic field has to be in this direction, has to be pointing to the left. So now use the right-hand rule to determine the direction of the current. Again, you place your finger or your thumb along the direction of the current that you think it's going to be in. Curl your fingers, and what you should get is that the current, I induced, should be in this direction here. All right. Thumb along the direction of I that I have here. If you curl your fingers, when your fingers are inside the coil, they're pointing in the direction of the magnetic field, which is pointing to the left. So that case is pretty simple. Let's have a look at our final case now. Okay, final case. Well, again, we start with a magnetic field produced by the bar magnet inside this coil region is pointing to the right. And in this case, we're going to move the magnet away from the coil. So we're going to give it some velocity, v, in this direction. So what is that going to do? That's going to make the overall field smaller. Okay? So that means that my delta B is really going to be in this direction. I'm making it smaller. I started with some initial B pointing to the right, and now I want the overall to be smaller. So I'm going to take some away. So what does that mean in terms of the induced field? Well, the induced field wants to keep the flux inside the coils the same. So that would have to be opposed to my change in B. This here always has to be opposite of my delta B. So now all we have to do is to determine which kind of, or which direction of current would produce an induced magnetic field pointing to the right inside the coils. Using our right-hand rule, you take your thumb, put it in the direction of the current, and you curl your fingers so inside the coil turns. Now my fingers are pointing to the right if my current is going down as shown in the figure here. So make sure you understand that part of it here. And that's it. Now we've covered all four cases. So you always start with just plotting what the field direction is inside the coil before you do anything. And then when you do move it, figure out how that's going to change the field. What is going to be the change in field? Is it going to get bigger? Is it going to get smaller? And then the induced magnetic field is always opposite of that change. And once you have the direction of the induced magnetic field, then you apply the right-hand rule in order to find which direction of the current would produce a field in the proper direction.